Okay.
Hello, everyone, and it's a great welcome to the Frontiers of Parameterized Complexity, and it's a great pleasure to introduce our speaker, Michal Pilipczuk, who will talk on Beyond the Sparsity. Welcome, Michal.
Yeah, thanks a lot. So I can speak now, and everybody hears you, right? Good, well. Okay, so thanks a lot for having me here and for allowing me to give this talk on this event, and thanks a lot for organizing this. I think it's a very good idea to bring us all together via this series of seminars. So today I'll be speaking about the topic that we were studying for the last few years together with several other people. Which is the theory of structural sparsity in graphs, and what can we do beyond this theory? What can we say about well-structured dense graphs? So before we start with the dense graph part, I need to give a short introduction to the theory of structural sparsity in graphs. I apologize in advance to everybody who knows this stuff and or have seen my talks before on this theory. This will be a little bit of repetition, but later on there will be a lot of new stuff as well. Okay, so when we are talking about sparsity in graphs, we first need to understand what does it mean that a graph that we are given is sparse. Yeah, so let's look at some examples. So definitely, if I'm looking at the graphs of maximum degree, say maximum degree 3 or 10 or maximum degree delta, they should be considered sparse, right? Well, for any reasonable definition of sparsity. And such graphs have a moderate number of edges in the sense that the number of edges m is bounded by the number of vertices n times delta half, right? Planar graphs should be also considered sparse. Yeah, you probably know that a planar graph on n vertices has at most 3 and minus 3 edges, and in every reasonable theory of sparsity, planar graphs should be also considered sparse, right? Another example of well-studied classes of sparse graphs are graphs of bounded tree width. Yeah, so if you've got tree width at most t in your graph, then the number of edges is at most t times n. This is also a model of sparsity that should be encompassed by our theory. Right, so we are now looking in this theory for some kind of a robust or efficient notion of sparsity. So what does this notion should have? We are looking for a notion of uniform sparsity in graphs. So we don't only want the number of edges to be linear in the number of vertices. This sparsity, I should not have any dense part in my graph. I cannot have like a small click with of size square root n with n vertices and otherwise small number of edges. Every part of the graph should be sort of uniformly sparse. Also, what I would like to have is that this notion should be robust or stable in the sense that doing some local modifications of my graph should preserve sparsity. Yeah, if I have a sparse graph and I say I contract two vertices onto each other, I should have maybe a little bit less sparse graph, but still this should count as preserving sparsity. Okay, so let's look at the other side of the spectrum. What should be dense graphs, right? So definitely, in any reasonable theory, clicks should be dense. They are as dense as they possibly as a graph possibly can be. But also say biclicks, they should be also considered dense, right? So they have quadratic number of edges, and therefore they should be complicated from a theory of sparsity. And in general, graphs with high edge density, like ratio between the number of edges and the number of vertices, they should be considered dense as well. Good. So then the classic notion of sparsity that is considered in, say, graph theory is the notion of excluding minors. So just to be on the same page, let me recall that a graph H here on the right-hand side, yes, is a minor of a graph G here on the left-hand side. If I can get H from G by contracting mutually disjoint connected subgraphs. Yeah, so as on the picture. Yeah, and this notion really extends this idea of planarity. The classic Kwiatkowski-Wagner theorem tells us that planar graphs are exactly K5, K3 minor 3 graphs. And there is a whole combinatorial theory around minor closed classes, with the most important result being the structure theorem of Robertson-Seymour, that morally says that if I fix some t, then essentially KT minor free graphs are topologically constrained graphs. They look more or less like this. They admit three decompositions into parts that are almost embeddable into some fixed surface. So this is very nice. This gives us some interesting combinatorial theory of minor closed classes. And that extends some of our examples. Yes, so for instance, planar graphs exclude K5 as a minor. Graphs of true with T, they exclude KT plus 2 as a minor. And in general, also excluding something as a minor gives us a constant upper bound on the edge density, right? So if I have a KT minor free graph, then the ratio between the number of edges and the number of vertices is bounded by T squared log T. However, the other example, graphs of bounded maximum degree, is not encompassed by this theory. Yes, so graphs with maximum degree 3, so subcubic graphs, they admit all cliques as minors. And to see it, it's very easy to see it. If I have a graph of high degree in a clique, I can replace it with a binary tree, which therefore has a maximum degree 3. And then contracting this subtree will give us back this vertex of high degree. Yes, so in a sense, excluding minors gives us some nice topological, interesting combinatorial theory, but this is not really the theory that we are after, yeah, because we would like this graph of maximum degree 3 also encompassed by our robust theory of sparsity, right? So looking at this example, at this blow up of this vertex of high degree into a binary tree, we see that in order to get this vertex of high degree, we would need to really contract a large binary tree, right? But we wanted to have to preserve the sparsity only under sort of like local operations, right? So maybe we should think about sort of a notion of local minors. And this is exactly what we are going to do. So I will say that H is a depth D minor of G, like on this picture, when I can obtain H from G by contracting mutually disjoint subgraph of radius at most D, right? So now I can contract not arbitrary connected subgraphs. I need to contract only local subgraphs of radius, say at most 10, if D is equal to 10, right? So this is a notion of sort of a local minor, or rather bounded depth minor. And I will denote it like that. H is a depth D minor of G. Right, so now we can formalize this intuition. The intuition is that sparsity should be exclusion of two dense structure at every fixed depth. So at depth 0, yes, I would like to exclude some dense structures, at depth 1 as well, and so on and so on. So we can now give the main definition of this theory of sparsity, which is the notion of nowhere denseness for classes of graphs. Yeah, so I say that the class of graph C is nowhere dense if for every fixed depth D, there exists a constant T of D, yes, such that the clique of size T of D is excluded as a depth D minor in every graph from my class. Yes, so whenever I take a graph from my class, I look at all the depth D minors of graphs from this class. I do not see a clique on T of D vertices from there. Yes, so the depth D minors of graphs from C, they exclude some clique as a depth D minor. Right, and so this was based on this understanding of dense structure as simply cliques. But now I can also think about dense structure as simply structures with too high edge density. And then I arrive at the notion of bounded expansion. So a class of graph C has bounded expansion if for every fixed depth, there exists a constant upper bound, C of D, for the edge density in depth D minors of graphs from C. So whenever I take a graph from C and I take a depth D minor of it, then I get a graph with edge density at most C of D. Yeah. So just to recap, the intuition is that nowhere dense means that at every fixed depth, I exclude some clique. And bounded expansion means that at every fixed depth, I exclude simply two dense graphs in terms of the edge density. Right, so it is clear that bounded expansion implies nowhere denseness, yeah? Because if I exclude two dense graphs, I definitely exclude some clique because clique have larger and larger edge density. The vice versa implication doesn't hold. There are classes that are nowhere dense but do not have bounded expansion, but we only know sort of artificial examples of such classes. And therefore, like most of the stuff that holds for bounded expansion classes also in some sense holds for nowhere dense classes. So note that here I made a sort of a conceptual shift in the sense that I defined sparsity as a property, as a feature, not of a single graph, but of a class of graphs. Yes, it is sort of meaningless to ask whether a clique on, say, 50 vertices is sparse or dense. But it's meaningful to say that, say, the class of all cliques is dense, and the class of all planar graphs is sparse, right? So you can think of sparsity as sort of a limit property of a class. Good. So these are the basic notions of sparsity. So let me now ask you, is this clear? And maybe I can see now in the chat if there are any questions at this point. Do I see the chat here? Sorry, I think I muted myself. Yeah. Now it's good. Okay. So did I miss much? Was it quick? Okay, I think it's good. So are there any questions about this definition at this point? Okay, if not, then I'm hiding that chat, and let's continue further. So this is the word of sparsity as we now see it, right? So at the top, there is this notion of nowhere denseness, which is the most general notions of sparsity in this theory. Then we have here some classes that we are not really concerned about. Here is this notion of bounded expansion below nowhere denseness, and this encompasses all the classic notions of sparsity in that combinatorially were studied, like excluding topological minor, bounded genus graphs, bounded degree graphs, and so on and so on. So these are abstract notions of sparsity that encompass much of the classes that were typically studied, right? And the really strong point of this theory is that there are multiple equivalent combinatorial characterizations of these notions that we just defined. So we defined nowhere denseness and bounded expansion in terms of sparsity of shallow minors, yes? But there are also multiple other characterizations. For instance, if you know the definition of the degeneracy, there are also proper generalizations of degeneracy to looking at every single bounded depth. They are called generalized caloric numbers, and they are very useful properties that can be used algorithmically, for instance. There's a notion of uniform quasi-wideness that morally says that in a large sparse graph, there are many vertices that are pairwise far from each other. There's also a VT dimension view on sparsity via those so-called neighborhood complexes, and many, many, many others. So all these notions that you see now on the slide, they are like tools that you can use for sparsity. They're equivalent characterization of bounded expansion or nowhere denseness, and each of these tools gives you a technique that can be used in the algorithmic context. So this sparsity as a field was initiated, let's say, 10 years ago by Jarek Neshachil and Patricia Sona de Mendes, and by now it really grew substantially and has found many algorithmic applications. Predominantly parameterized algorithm, but also approximation algorithm, distributed computing, and descriptive model theory. And during this talk, we will focus on the first and the last, parameterized algorithm, and blend with descriptive model theory. And as I said, essentially this field is a very parameterized field in a sense. Even if you are not after a certain parameterized algorithm, an FPT algorithm, you really work with parameters all the time, because all the sparsity of shallow minors or generalized coloring numbers, these are very parameterized in spirit. And understanding and experience with parameterized complexity really gives you an edge. Yes, so the toolbox is very robustly working on bounded expansion classes. It is a little bit more technical in the lower dense setting, but most of the stuff can be lifted to this setting as well. So I will not go much further into this theory because we want to go beyond sparsity. But if you want to know more about this theory, and I really recommend that you do, because it's a really cool field. There is a monograph by Nasha Chile and Osana de Mendes. However, it was written in 2012, so quite a long time ago. It is already a little bit outdated. But together with Sebastian Siebert and with my brother Marcin, we gave twice a course in Warsaw about it. You can find lecture notes on these web pages around here. And there are also YouTube videos of our lectures, so I recommend looking at them if you want. Good, so let's look at some parameterized application of this toolbox. And we will be looking at dominating set problems, which are the problem that we love the most in sparsity. So I guess that most of you have already seen the dominating set problem. I'm given a graph G and a parameter K, yes, and the question is whether I can cover the whole graph using K neighborhoods of vertices. Yes, so I want to find a set D of K vertices, so that if I take the union of their close neighborhoods, I get all the vertices in my graph. I will looking at a certain generalization of this, namely distance D dominating set problem. So instead of every vertex dominating itself and all its neighbors, let every vertex dominate itself and all the vertices that are at distance at most D. Yeah, this is a natural generalization. So for instance, on this graph, you can see that there is a distance-free dominating set of size 4. Each of those vertices that is highlighted dominates a ball of radius 3 around it, and all the vertices get dominated. Yeah. Quick riddle for you. What city is that? So what about the parameterized complexity of distance dominating set problem on sparse classes? So apparently these notions of lower dense and bounded expansion are really well suited for the treatment of this problem. So what we proved some time ago is that whenever you are having a bounded expansion class C, you can find a linear kernel for distance dominating set for every fixed D. And whenever you have a lower dense class, then you can have a almost linear kernel. So a kernel of size K to 1 plus epsilon for any fixed epsilon that you wish for. Yes, on the graphs from C. Yeah, so this is very nice. This very nicely explains the parameters complexity of the distance domination on sparse classes. And actually, this is tight. Whenever you have a subgraph closed class that is not lower dense, in the sense that it is somewhere dense, then distance dominating set on this class is already W2 hard. So this means that nowhere denseness is exactly the limit of tractability of dominating set, at least on subgraph closed classes, right? So really distance nowhere denseness is the border of the tractability. Below it, I even have an almost linear kernel. Above it, I am W2 hard, right? So the idea is that why this worked is that because dominating set is sort of a local problem. And our toolbox of sparsity is tailored to local minors, and therefore it provides tools for local problems. So what other local problems I do have in parameterized complexity? Well, I can give a meta answer to this question, namely all problems that are expressible in first order logic are sort of local. And this is a well-known fact about first order logic that we will review in a moment. So to give you a recap what is first order logic, I will not define it fully formally, I just give two examples. So for instance, in first order logic for two vertices x and y, I can write a formula for every fixed D. I can write a formula that the distance between those two vertices is at most D. How would I do it? If, for example, if I want to say that the distance at most free, I would say that there are two middle vertices, Z and W, and there are edges between X and Z, Z and W and Y. Yeah, so I just quantify existentially a path of length 3. Yeah, well, actually, maybe there are distance 2, so I need to take care of this. Then I do this recursive definition that delta 3 is equal to delta 2, or there exists a path of length. I hope that this is clear now. Then, for instance, I could write a sentence now, so a formula without free variables, without this X and Y, that expresses that in a graph, I have a distance D dominating set of size K. Yeah. How would I do it? I would just say there is a first vertex, there is a second vertex, there is a K vertex from my dominating set, such that for every vertex Y, it is at distance at most D from one of the X size, right? So this is, now I wrote this formula phi of dk based on the formula this delta D. Yeah, so you can see more or less all the features of first order logic that you can use. You can check whether two vertices are adjacent. You can existentially quantify and universally quantify vertices. You can use Boolean connectives. Something that you did not see here, but you can also use is negation. Yeah, you can negate for it. And more or less, first order logic cannot do much more. Yeah, so morally, the theorem of Geifman tells you that first order logic is local, in the sense that it cannot do much more than essentially say that two vertices are close or far from each other. I will not give the formal statement of this result, but this is the feed, right? So now you can ask yourself, okay, so this works for dominating set problem, which we see now that can be phrased in first order logic. Can this happen for every problem that is expressible in first order logic? And this brings us to this formal problem of first order model checking, where I'm given a graph, yes, and I'm given a problem expressible in first order logic, which is expressible by a first order sentence, yes, that says something about the condition that should hold in a graph, and I need to check whether indeed in this graph this formula, this sentence holds, right? And I would denote it like this, which should be read by as G is a model for phi. Yeah. So this problem you can solve easily in XP running time, essentially by brute forcing every quantification. Whenever you have a quantifier, you just you say there exists a vertex, you just branch into all the possibilities, and the problem is AW star complete, so probably no FPT algorithm. And indeed, in sparse classes, you can make a meta theorem, a meta algorithm for all the problems expressible in first order logic. Yeah, so this is a theorem of Dvorak, Real, and Thomas for bounded expansion, and of Groer, Kreutzer, and Siebert for nowhere dense. Then this problem, parameterized by the formula, by the sentence phi provided on input, is linear time FPT on bounded expansion classes and almost linear FPT in nowhere dense classes. Yeah, so every problem that you can express in first order logic, you can nicely in FPT time solve on sparse graph classes, provided that the parameter is the length of the formula. And actually, this is tight. On subgraph closed classes, if your class is not nowhere dense, it is somewhere dense, then FO model checking is as hard as on general graph. It is AW star. So this means that really for this meta problem of solving all the FO, every fixed FO definable problem, nowhere denseness really delimits the tractability region from the parameters complexity perspective. Good. So are there any questions at this point? Okay, so if not, let me go further. Okay, so for this FO model checking on sparse graphs, we have by now a very robust understanding of this FO model checking algorithm, and it can be extended to several other variants of the problem. For example, you can count the number of solutions in both cases. You can do query enumeration, so you can like list all the solutions to some FO definable problem. You can implement this, at least on bound expansion classes, in sort of a low circuit complexity. You can do some sort of a partial dynamic setting, which gives you a data structure that can tell you whether a sentence is true or not under some changing like dynamic modification of the structure of the graph. All of this is very satisfying and gives us a very robust understanding of this FO model checking. However, there is one but. Yeah, what about this assumption of subgraph closeness? Yeah, so we assumed we have shown that this theorems give you robust FPT algorithm on subgraph closed classes whenever the graph is nowhere dense. But are there any, say, non-subgraph closed classes of dense graphs where actually FO is also tractable, right? So yeah. And the obvious answer is obviously yes. For instance, on the class of all clicks, yes, FO model checking is trivially tractable, because whenever I'm asking you, is there an edge between two vertices? Well, the answer is always yes. Yeah. More generally, like when I take any nowhere dense class of graphs and I take the class of its complements, then FO model checking is also robustly tractable, because if I want to check some formula, some sentence on the complement of some graph, it's just, I can just complement the graph back, and I get a sparse graph on which I can model check an adjusted formula, where I just replace adjacency with negation of adjacency, right? So these are a little bit stupid examples. However, there's one much more worrying example, namely classes of bounded click width, right? So just to recall, click width is a width parameter of a graph. It is defined by looking at those k-labeled graphs. So a k-labeled graph is a graph where every vertex is given a label from 1 up to k. And on this labeled graph, I've got some basic algebraic operations. For instance, I can take two vertices, two labels, say the blue label and the red and the yellow label, and can put all possible edges between them. I can also do renaming. So for instance, I can merge the yellow and the blue label. And I can take the disjoint union of two labeled graphs. Yeah, and in this way, you can construct larger and larger graphs. And the click width is the minimum number of labels that you need in order to construct a graph from single vertex. And the intuition is that this way of constructing can be written as a algebraic term, which is called the K expression. And this gives you sort of a tree-like decomposition that describes the structure of the graph. Yeah, and this notion of click width generalizes the notion of tree width, in a sense that if a class has bounded tree width, so there's a universal bound on the tree width of all the members of my class, then the class has also bounded click width. Yeah. However, graphs of bounded click width, they can be dense. For instance, I can add a super large biclick somewhere there in my graph. Yes. And actually, on classes of bounded click width, you can do also FO model checking in parameters in FPT type, right? And the idea of the proof of this is you transform, for instance, you essentially run a dynamic programming. You can cast it as a run of an automaton or evaluation of some algebraic term. But the underlying reason behind this tractability is the fact that FO is compositional, in the sense that if you understood some FO sentence on one part of the graph and you understood it on the other part of the graph, and you combine these two parts in a homogeneous way, in a sense, you either put all the edges between or no edge between, then you can understand the FO sentence on this combination. Yeah, so this is basic notion called compositionality. Yes, so this means that graphs of click width at most k for every fixed k is a class of dense graph on which FO is tractable. It is not subgraph closed, and therefore the dichotomy theorem that we have seen earlier doesn't apply to this. Yeah. So how do we combine this with our understanding of first order logical sparse graphs? Yeah. So to put it in a more illustrious way, on one hand we have got bounded click width, yes, where the reason for tractability is this compositionality. On the other hand, there is nowhere denseness, where the reason is sort of locality. This is at least our understanding. And we would like to get a common reason why FO is parameterized tractable in classes of graphs. So how do we combine these two notions? Yeah, you can of course combine it in a sort of a forceful way, but as you see here, probably if you do it, the outcome might be not mathematically the most satisfying. Yeah. So what we want to do now is to develop a theory that would explain when and why FO model checking is structured. And this is what this beyond sparsity program is actually about. So let's try to proceed by the means of analogy. Yeah. So for minor closed problems, we looked at classes defined by forbidding minors, a minor closed class. And this was well suited because like minor closed problems are topologically constrained in a sense, and the minor order is therefore the right tool to analyze them. Yeah. If we are looking at local problems on sparse graph, we are looking at those classes defined by forbidding shallow minors, because the shallow minors really capture the essence of local modifications in the graph. So what should we choose if we want to study all FO definable problems? We should choose classes that are defined using some sort of a containment notion that is suited for first order logic in general, right? So we would like to devise a new containment notion for FO definable problems and start to build a structural theory around it. Yeah. And this notion will be called FO transductions. And these are basically graph transformations that are definable in first order logic. Yeah. So in a nutshell, what we will be doing, we will be taking FO transductions and non-deterministic coloring plus a one-dimensional FO interpretation. For those who know what does it mean, but we will go slowly through some examples in a minute, and then through formal definitions to see what this means. Okay, I need to start with FO interpretations. Yeah, so let's look at two examples of FO interpretation before we get to formal definition. So one very basic FO interpretation is one that we have seen already, namely taking in the complement of a graph. Yeah, so if I have a graph, its complement is a graph on the same vertex set where I put an edge, if and only if there was no edge before. Yeah, so there in the new graph, two vertices are adjacent, if and only if they were not adjacent before, right? Another basic FO interpretation is taking a power of a graph. So the d power of a graph G is the graph G to the d, which is a graph on the same vertex set where I put an edge if and only if two vertices were at the distance at most d in the original graph. Yeah, so for instance, this is a square of a graph on the left-hand side because I'm putting in all the original edges plus all the edges between vertices of a distance at most 2. Yeah. So from these two examples, you can already probably deduce what is an FO interpretation. An FO interpretation is a pair of formulas: alpha, which will define the domain of a new graph, and phi, which will define the new edge set. And essentially, if I've got a graph G, I can put this graph G through the interpretation, and I get a graph that is defined as follows. The edge set of the new graph is defined exactly using the formula phi, right? So I put all the edges whenever the formula phi was true. Yes. And this formula alpha is used to sort of restrict the vertexes of my graph. Yeah? So I restrict the vertex of my graph to all the vertices that were that satisfy the formula alpha. Yeah. So in these two examples, actually alpha was always true. Yeah. So I did not restrict my vertex at all. Yeah. But in general, I can also restrict my my vertex set to some subset that is defined via some FO. Good. So is this clear? Are there any questions at this point? Good. No questions at this point. So let me go further to the notion of FO transactions. So this will be not much more complicated. I will just add one more element, which is a non-deterministic coloring of my structure. Yeah. So a colored graph is simply a graph with some number of distinguished subsets of vertices. So for example, I can have a graph and there will be a subset of blue blue vertices and the subset of red vertices. Yes? And the fact that there will be blue vertices and there will be red vertices will be given by this monadic signature. So monadic signature is just a set of names. Yes, the set of names that there will be blue vertices and there will be red vertices. And then a sigma colored graph is simply a graph with the evaluation of this red and blue. Yeah. So an FO transduction is a pair consisting of a monadic signature, so a set of names essentially, red, blue, and so on. And then an FO interpretation that takes this colored graph with those names and outputs a graph. Yeah, so now formally this FO interpretation can also look at the colors of vertices. So how can I run such a transduction T on a graph G? First, I take my graph G and I non-deterministically put those colors there. Yes, so I guess what will be the red vertices, what will be the blue vertices, and so on and so on. And then I just apply my interpretation to this obtained colored graph, and I get some result. And then the T of G, the transduction applied to G, is not a single graph, as was the case for interpretations. It's actually a set of all possible graphs that I can obtain in this way. Yeah. So to give you some example, if my sigma consists of the set of red vertices, and my interpretation J is square the graph and restrict the universe, the vertex set, to the neighborhood of red vertices, then a possible run of a transduction on this graph would be as follows. For instance, first I choose non-deterministically my red vertices. Yeah. Then I take the square of the graph. Yeah. So this is the square of the original graph. And finally, I restrict my vertex set to a subset of vertices that were neighboring the red vertices in the original graph. Yeah. So this graph on the right-hand side would be one possible outcome of running the transduction T to the graph on the left-hand side. Of course, for other choices of the red vertices, I could get different outputs at the end. Yeah. So this is a transduction. Are there any questions now at this point to the notion of a transduction? Okay, good. So let's look at this notion of a transduction as a containment notion for graphs. Yes? So you can easily prove, this is not too hard, that FO transductions are closed undertaking composition. Yeah, so this is already a very good sign that this is a well-suited notion of a well-suited containment notion. They are also very nice with respect to first order definable properties. Whenever something is defined via an FO sentence in the output of a transduction of an interpretation, then it is defined that it can be defined already in the preimage of the interpretation in the following sense. If I've got an FO interpretation and I've got an FO sentence, say psi, yes, then I can pull back this sentence through the interpretation as follows. I can get some sentence that works on the original graph that is true if and only if the sentence psi was true in the image. Yeah. So this, you have already seen this proof before. Yes. In this, when I was talking about FO model checking on graphs and complements. Yes. To get this pullback of the formula psi, what I need to do whenever I'm checking the two vertices are adjacent in the image of the interpretation, what I need to do in the preimage of the interpretation, I need to check whether this formula phi that defined the new edges was true. Yeah. Oh, you need to take care also of this restriction of the vertex set. So whenever the formula psi is saying there exists a vertex, the formula pulled back need to say there exists a vertex that additionally satisfies this all. But that's essentially it. Meaning this is a syntactic change of the formula psi, right? So now you can think of transductions as mapping not simply graphs to sets of graphs, but actually as operators on classes of graphs. Yeah. So if you have some class of graph C, you can apply the interpretation T to it and get a new class of graphs that consists of all possible images of all the graphs from C under this transduction. Yeah. So this, you can now think of this as a transformations on classes of graphs. Yes. So now the nice thing about this is that this backwards translation lemma that we have seen before essentially tells you that the model checking problem on the image of a transaction is not much harder than the FO model checking problem on the original class. So in this sense, you can translate, you can generalize FO model checking results from classes of graph to their closures under undertaking transactions. So suppose that that I've got some class C and I've got some transaction T, yes, and I've got some graph H from the image of the transaction, and I've got some sentence psi that I would like to check whether it's satisfied in H. So what do? I simply know that there is a graph G from my original class. Well, it is colored, yes, such that H is the image under my interpretation of G. Yeah? And then in order to check whether in H phi holds, I just need to check whether in G, yes, this pulled back formula holds. Yes? And this is exactly this proof that we had in about the complements. Yes, in order to check whether some FO sentence is satisfied in the complement, I need to complement the graph back, and I need to pull back the formula. Yeah? There is one catch here, right? I said there exists a graph G, such that H is the image of G. Yeah? However, getting this pre-image algorithmically can be computationally hard. Yeah. So for the complements, it was very easy because I can just complement the graph back. But even for taking the power of a graph, finding the pre-image undertaking a power is a computationally hard problem. Yes. So this reduction works only if the pre-image can be computed efficiently. And one more technical drawback is that we actually need to assume that we can solve the FO model checking problem on colored graphs in my original class. Yeah, but this is usually the case, and this is usually a non-issue. However, getting the pre-image efficiently is truly a problem. However, still there is this intuition prevailing that if you take a class on which you know that FO model checking is efficiently doable, then the closure of this class under some transaction is also a class where you should be able to say something meaningful about FO model checking. At least this is a class that is a good candidate for finding FO model checking results. And even if C is sparse, T of C can contain dense graphs, and therefore it is meaningful to look at the problem there. So another idea here is that FO transaction can be used as to define abstractions for having good structure in a graph. Yeah, because essentially it is a containment notion, exactly as before. Yeah. So for instance, again by analogy, if my class is how I define that the class is nowhere dense, I said that for every fixed depth, yes, I exclude some clique at this depth, right? At every fixed depth, I excluded some too complicated structure. So now to define the same thing for the structural theory based on FO transaction, I would say that the class D is well structured if for every transaction T, T of D excludes something. Yeah. So now we have a good notion of containment. Around this notion of containment being FO transaction, we can try to build some theory. And we need to find the good abstractions that will define our theory in a robust way. Yeah? So what should we put as this something to get a compelling mathematical theory? Okay, before we get to these abstractions, are there any questions at this point? Okay. So if not, then we move on to trying to get the right notion of abstraction. And for this, we will look at the different fields of research, namely model theory. So in model theory, like looking at dividing lines between things that are simple and things that are complex is something that people are studying for years. And the two main notions there that are used are called stability and dependence. So without going into details and without giving like formal details, essentially a model, think graph, an infinite graph actually, is stable if for every fixed FO formula, I cannot, using this formula, I cannot define too large, arbitrarily long linear orders. So linear orders is a reasonable notion of an abstraction. And similarly, a model M is dependent if for every formula, I cannot interpret arbitrarily large power sets in this graph. Yeah, power sets being like bipartite graphs where I have here some subset on vertices, and on the other side, I've got 2 to the n vertices for each possible adjustment on the other side. Yeah. So stability implies dependence. This we will see in a moment in more details. We will not go into the details of this definition, and this is a vast oversimplification of what actually is happening in stability. However, this is the intuition that good people in model theory, after years of studies, concluded that linear orders and power sets are 2 good abstractions to devise a nice structural theory. Yes, so this stability is a model area of model theory, studying these notions since the 60s. These are fundamental concepts with many structural characterization, like forking, ranks, indeterminate sequences, number of types, and so on and so on. So similar to sparsity, we have a lot of structural characterization that are equivalent and give you different tools to study these notions. And the problem is that a priori, the whole theory is inherently infinite, yes, infinitary in nature. However, when you look at a bit closer, actually there are many combinatorial arguments there, combinatorial reasonings that you can lift to the finite, and you can actually think of them as sort of algorithmic ingredients that you can apply to different things. Yes. So the idea now is to use orders and power sets as abstractions under FO interpretation, and try to translate all the toolbox from the stability theory to the finite. Yeah. So the key here is to get the right definitions. Yes, to get the right definition of what dependence and stability should say in classes of finite graphs. So for this, we will talk about half graphs and power set graphs. Yeah. So a half graph is the graph that you see here on the picture. Yes. So a half graph is like bipartite graph with A1 up to AN on one side, B1 up to BN on the other side. And I put an edge between AI and BJ if and only if I is smaller than J. Yeah. So this is really a graph that sort of encodes linear order. And this is the intuition from the stability that these are good structures to exclude. And the power set graph is something that I already defined before. On one side, I've got n vertices. On the other side, I've got 2 to the n vertices. And for each subset of the one side, I've got a vertex that sees exactly this subset. Yeah. So I will exclude those 2 structures as sort of semi-induced subgraph. So semi-induced subgraph is nothing to be very scared about. This is just an induced subgraph where I care only about the adjacency between two sides, right? So I've got here a subset of vertices A prime. Here I've got a subset of vertices B prime, and I say that this is a semi-induced subgraph of H if the induced edge relation between the 2 sides is exactly as in H. Yeah. So in other words, it is like induced subgraph. It's just that I do not care about the adjacencies within A and within B. Good. And now, with this notion, we can define what does it mean stable and dependent for classes of graphs simply. This is so far a purely combinatorial notion. A class is dependent if it excludes some power set graph as a semi-induced subgraph. So I say I exclude a power set graph of size 10, of order 10. It is stable if I exclude some half graph as a semi-induced subgraph. And it will be also good to introduce this notion of being quickly sparse. This just means that I exclude some biclic. As a semi-induced subgraph, this is the same as saying I exclude this as subgraph. Yeah, so far, this is a purely graph theoretical notion of just saying I do not see 2 large half graphs in my class, or I do not see 2 large power subgraphs in my class. And now I can apply this principle of transactions to it. I will say that a class of graphs is monadically dependent if for every transaction T that I can apply to my class, I get a class that is simple in the sense that it doesn't have too large power set graph. It has a dependent edge relation. And the class is monadically stable if for every transaction T, if I apply this transaction to my class, I get a stable edge. I get a class with stable edge relation. So a class that doesn't have too large, it doesn't have arbitrarily large half graphs. Yeah. So what happened here is exactly this intuition that we had in lower denseness. We just replaced the notion of shallow click minors with the notions of excluding half graphs and power set graphs under transaction. Yeah. So now we would like to understand the theory, the structural theory behind these two notions. Okay, so are these two notions clear at this point? Are there any questions? Where does K, L, J, free subgraphs belong? If it all belongs somewhere. Yes, so this graphs that exclude some biclicks as subgraphs, they are weakly sparse. Yes, and they are also have stable edge relation, and they also have they are also dependent. So weakly sparse, like because a large half graph contains a large biclick, like weakly sparse is a more restrictive notion than having a stable edge relation, which in turn is a more restrictive notion than having a dependent edge relation. Yeah. However, like Kij free graphs are not necessarily monadically stable, because then in monadic stability, I require that this happens under every transaction, not just in the class, but under every transaction as well. Did I answer your question? Yeah, good. Are there any questions at this point? Good. Let's go further. So we have now two good notions of good structure in graphs. We can compare it to some other notions. For instance, if you look at the learning theory, these notions of dependent edge relation and stable edge relation were actually already studied. Like dependent edge relation is essentially the same as bounding the fifth dimension of a graph. And stable edge relation was in the 80s defined as so-called bounded Littleton dimension there. Yeah. So what about sparsity? Yeah. So how these new notions compare to the notions in sparsity? And actually they compare a lot. It turns out that every nowhere dense class is monadically stable. So this is super nice. Yeah. So indeed, nowhere denseness extends monadic stability extends nowhere denseness. So we have a proper extension of our current theory of sparsity. And even more, if you assume that your graph class is subgraph closed, then monadic dependence and monadic stability collapse to nowhere denseness, right? So the idea is that we have now a notion that extends our sparsity theory that sort of collapses to sparsity if you assume subgraph closures. So maybe this monadic stability and monadic dependence, yes, is a notion that sort of like our understanding of sparsity is just a shadow of a more general theory. Yeah. On the other hand, classes of bounded click width are actually monadically dependent. Yeah. So this monadically dependence also extends our other point of view, the bounded click width point of view. Bounded click width classes are not necessarily monadically stable just because half graphs themselves have bounded click width. Yeah? So the picture looks like that. Yeah, we've got bounded tree width classes and bounded click width classes that extend them. We've got our notions of sparseness. Yes, weakly sparse, nowhere dense, bounded tree width. And then we have two more general concepts. We have this stability level and this dependence level, and we've got inclusions as shown on the picture. Yeah, so you see here that this monadic dependence, it generates both bounded click width and nowhere denseness, right? So now if you want to combine bounded click width and nowhere denseness, yes, instead of trying to forcing these two notions into one notion in a sort of artificial way, we have found one notion, yes, that sounds reasonable And from one point of view, it looks like bounded click width. From the other point of view, it looks like nowhere denseness. So it seems that maybe this actually leads to some robust mathematical theory that can explain FO model checking. So now we have a very precise conjecture, yes, that FO model checking should be FPT on every monadically dependent class or every monadically stable class of graphs, and we are still very, very far from getting this understanding. Yeah. So the first goal in this theory would be to get a good structural understanding of this monadically dependent stable classes. So we would like to have like analogs of the structural tools from Sparsity, like uniform quasi-wideness, generalized coloring numbers, all of this stuff, because we are really lacking tools there, structural tools to analyze and to get algorithmic results. Yes. And the hope is to get those tools, the infinite tools from stability, and try to translate them to the finite. But this is very hard work. This is very complicated. And unfortunately, even though this is like the number one goal that we need to look at this point, I have hardly any progress that I can report at this point. Another goal would be to get some algorithm using those stability tools. Yeah. Here, there are already some algorithms that it can give. For instance, at Stacks last year, we gave a very nice algorithm for the dominating subproblem in powers of nowhere dense class. So not necessarily all monadically stable, but still more than just nowhere denseness. And the algorithm actually doesn't need to know the preimage. It can just run on the graph, yes, without knowing the preimage, and just from the structural properties of the class, we get that it runs in FPT type. Yes, and one notion that I would like to finish with at this point is to investigate, like, look at classes that we know that are well behaved, for example, sparse classes. Yes, and close them under FO transductions and see what we get there and what kind of nice structure we can get there. Yeah. So, for instance, like how we can formalize this, if I take a class of classes of graphs, I will call this variety. For instance, like nowhere dense is a variety of classes of graphs. I can close this this variety under FO transduction in the sense given on the slide. Yeah, I take all possible transactions and I take all subclasses of those. Yeah. And we usually talk here about, say, for instance, structural bounded expansion classes. These are class FO interpretations of classes of bounded expansion. Yeah. So the idea would be to look at sparse varieties like bounded expansion classes, close them under FO transaction, and see what animals do we get. Because in these animals, we hope to find good FO model checking tractability results. And also, we are actually curious what kind of structure we can quantify there. Yeah? In both cases, we need some circular understanding. So let's look at one fixed example, for instance, structural bounded tree-width class. What are those? Good. So on one hand, yes, structural bounded tree-width classes, there are also bounded click-width, yes, and bounded click-width are closed undertaking FO transductions, yes. So structural bounded tree-width wouldn't be more than bounded click. On the other hand, structural bounded tree-width are monadically stable, and monadically stable also closed undertaking FO transduction. So I will not get anything more than monadically stable in this process. Yeah. So I see that structural bounded tree-width is in the intersection of bounded click-width and monadically stable, and actually it turns out that this is the same. Yes, that structural bounded tree-width is exactly bounded click-width intersection monadically stable. And I can even only assume that the edge relation is stable. So in here, between bounded tree-width and bounded click-width, we can put one more class, structural bounded tree-width, which is exactly the same as bounded click-width and stable edge relation. And now we can start to explore this diagram. For instance, for these two classes, we can see that nowhere denseness is exactly weakly sparse intersection monadically stable. And you can prove, and this is a non-trivial proof, that actually monadically stable is the same as monadically dependent intersection stable edge relation. You can add also bounded path width to the picture. And again, here, if you have one of those concepts on the diagram, it's actually an intersection of the two neighboring concepts. Yeah? So you can see a very nice structure of classes here. But there are, of course, many, many more classes of sparse that we can investigate. For instance, bounded expansion, bounded degree classes. You can also close them under FO transductions, get structurally bounded expansion classes, structurally bounded degree classes. And now the question would be, what are those? Yes, how can you quantify the structure there? So without going much into the details, actually during the last few years, we managed to get a good structural understanding what are structurally bounded degree classes and structurally bounded expansion classes in terms of precise combinatorial characterizations. In the setting of structurally bounded degree class, this actually gives us FPT model checking result. For structurally bounded expansion classes, unfortunately not, because the characterization is purely combinatorial and existential. Yeah, we do not know still how to get the preimage, which would be necessary for getting the FO model checking tractability. Good. So let me only give you one other possible application of this whole framework, namely, if we are talking about combinatorial properties of classes, yes, we can also think about other indicators of well-structuredness in classes of graphs. You can look at Vapnik-Cherveninki's parameter, like VC dimension. So monadically dependent is basically like bounding VC dimension, and however, in structurally nowhere dense, even we have much better understanding. The so-called VC density is almost linear. Yeah. So this is the degree of the polynomial in the Sauer-Shell lemma. You can also have nice application for the Erdős-Hajnal property. In stable edge, when you have stable edge relation, you have Erdős-Hajnal properties, a very nice proof of Meliaris and Shella. In structural bound expansion, you've got even strong Erdős-Hajnal. In structurally lower dense, you have almost strong Erdős-Hajnal. This is a new result that we came up recently with Marcin Brianski, Piotr Micek, and Michał Pilipczuk. You also have some interesting properties for high boundedness. So just to conclude, let me conclude with several concrete open questions in this direction. So the first one, which I want to reiterate, FPT model checking on monadically dependent classes. We hope that this is true, and this would be great if we get this. Yeah. Another conjecture that you can post here, if you look at this diagram before, we actually do not know whether structurally nowhere dense is the same as monadically stable. Yeah. If we got this, this would be great, because then every monadically stable can be sort of seen as a sparse class under some transaction, and we would get a very nice structural understanding of monadically stable classes. For structurally nowhere dense, we actually have a very good conjecture about what the structure should be. This should be phrased in terms similar as structurally bounded expansion in terms of admitting low sharp depth coloring. And we hope that this is the most feasible of these goals, and this would provide us very nice structural combinatorial results on structural nowhere dense classes. Another two directions that you could name here, when you talk about bounded click width graphs or bounded rank width graphs, there is a parallel combinatorial graph theory of vertex-minors that is tailored to those classes. So if you want to extend this theory to, say, more general classes, it is natural to investigate the concept of, say, shallow vertex-minors. Maybe this works. I know that some people were looking at it. It would be nice to investigate whether it actually makes sense. Another direction is recently, there was a very nice paper about, like a month ago, it appeared on RHEP about the so-called twin width parameter, which is also a parameter about graphs that gives you tractable FO model checking. It's sort of, at first glance, it's sort of an animal from another zoo, in the sense that it behaves sort of in a different way. However, it is definitely very interesting to see how this fits into the picture. Yeah. So let me conclude here. Big thank you to all my co-authors, especially Sebastian and Szymon, with whom we worked a lot on this concept, and to Felix for all the nice pictures that we have in that I had in the stock, and also to Michal Pilipczuk for the beamerings, the nice template in which this presentation was given. Good. Yeah. So thank you for your attention.
And thank you very much, Miko, also for a nice talk. Yes.
So are we taking any questions now? I guess I can.
I think it makes a lot of sense, right?
If there are any questions, I am more than happy to discuss.
Yes. From Manuel Sorge, there's a question. Thanks, Miko. Do you have some more non-trivial useful examples of FO transactions?
Sorry, I just got. Do you have more non-trivial useful examples of FO transactions? You mean besides taking power, besides taking complements, and so on and so on? Yes. I would need to think about it. Yeah. So one example that we are always using in papers is the class of map graphs, which are intersection graphs of closed regions in the plane, and they are contained in squares of planar graphs. There are subgraphs of squares of planar graphs, and a lot of these tools apply as is in map graphs. For instance, using this toolbox this algorithm for the dominating set problem, it also works on map graphs. So you can get an FPT algorithm for the dominating set problem on map graphs without computing the pre-image planar graph, the map embedding. You only use the structure of the planar graph. However, I would need to think if I have any concrete example that is not really tailored to taking powers. I don't think that actually it will be easy to find one, because as I said, essentially what first order logic can do on graphs is taking powers and doing complements. So in a sense, this is just the curiosity of how far and how robust mathematical theory we can get around FO model checking. Yeah, I hope that this sort of answered the question. I'm not sure. Yeah, good. Okay, any more questions?
Can you maybe comment why you call twin width animal from another zoo? So why is so different?
So the thing is that it fits sort of in a perpendicular way, in a perpendicular way into the hierarchy that we see at this point. Because on one hand, graphs, subcubic graphs do not have in general bounded twin width. So so it is definitely sort of lower than bounded degree graphs. And on the other hand, there are classes of expanders, of subcubic expanders that do have bounded twin width. Yes. So in a sense, it sort of carves the class of bounded degree graph in half, which sort of indicates that it sort of measures a little bit of different property. So I'm not sure if I have, meaning we are looking at this twin width parameter quite a lot recently, and I'm not sure if I have a good intuition about it at this point, but it sort of also takes care of symmetries in the graph. And this is something that is completely not visible in the theory of sparsity or in the theory of beyond sparsity.
Okay, I see.
Yeah, but it's very interesting to see what we can get from there, because like the model checking algorithm for graph bounded twin width is sort of based on locality and sort of based on compositionality as well. And it is very interesting to see and how this very nice framework of the FO model checking on bounded twin width fits into how we understand FO model checking in sparse graphs or in bounded click width graphs now. Yeah. Good. Any more questions?
Okay, Michal. So then I just thank on behalf of everyone you once again. Yes.
Yep. Thanks a lot for having me.
Yes.
Yep.
Thanks again and bye. Take care.
Yep. Okay. See you.
Bye. Yes.